In this session, we'll discuss about design for test. The design flow that we have seen describes the architecture exploration and proceeds through to delivery of design rules for manufacture of ASICs or programming of FPGAs. Then once the chips have been manufactured, they must be tested to ensure that they work correctly. There are several reasons why manufactured chips might not work, including problems arising during wafer manufacture and during packaging. Some problems cause whole batches of chips to fail, whereas others produce isolated failures. The aim of testing after manufacture is to identify the defective chips so that they can be discarded rather than supplied to customers. In case of ASICs, developing tests for developing tests for the chip is part of the design process. The design for test can reduce the time and cost involved in testing a system by including additional circuitry to improve the system's testability. Such circuitry includes elements that make internal nodes observable or that perform testing automatically as a sequential mode of system operation. Design for test, also known as DFT, refer to design techniques that, that seek to improve the testability. DFT, design for test, can be classified into fault models and fault simulation, scan design and boundary scan, built-in self-test. Fault models and fault simulation. It's a choice over the requirement. As a part of a design flow, we need to develop a set of test vectors or test patterns, that is combinations of input values for the circuit that can be used to expose faults. The idea is that application of each test vector should cause the circuit to produce a given output. If the circuit produces a different output, the circuit is faulty. A good choice of vectors may also be able to locate the fault within the circuit. In order to work out how to expose faults, we need to consider the kinds of faults that can occur in a circuit. We depend on fault models that are abstractions on the effects of the effects produced by the faults. We use fault simulator that simulates the operation of circuit with a given fault injected at a given location. The fault simulation is the simulator is something like it's similar to the simulator. The simulator applies test vectors until an incorrect output results, indicating that the fault has been detected. If no incorrect output is produced for all of the test vectors, the fault remains undetected by the set of vectors. The simulator repeats the simulation of other faults and other locations in the circuit. Once all of the faults have been simulated, the fault coverage of test vectors, that is, the proportion of faults detected, can be determined. Next one is fault model. So in choosing the test vectors, we can use an automatic test pattern generator. It's an EDA tool that analyzes a circuit and seeks to create a minimal set of test vectors with as close to full coverage as possible. A simple and commonly used fault model is the stuck model, in which an input or output of a gate in a circuit can be stuck at 0 or at 1 rather than being able to change between 0 and 1. Such a fault might be caused by a short circuit to the ground or power supply. Here, the figure shows A, B, C are inputs. BC input forms its input for the OR gate, and the output of OR gate is stuck at 1. Stuck at 1. Now, irrespective of irrespective of the A input, the output of OR gate is 1. So, at any case, the Z is depending on the stuck at 1 input. So such circuit we call it as stuck at 1. Similarly, we can have stuck at 0 at any input or at any net connection. The particular point can be connected to 0, or if it is shorted to ground, that we call it as a fault in the circuit that makes the output is incorrect. So this is one kind of fault model. So in this case, the input of the AND gate is might be shorted to VDD or logic 1, so that Z is depending on the stuck at 1 irrespective of value of A or BC. Similarly, another kind of fault model, it is transistor level circuit for gates. Consider a circuit. In this circuit, in case if a transistor, a pull-up transistor PMOS, if it is on, if it is stuck on, then irrespective of input applied to the NMOS input, the output is depending on the pull-up transistor. Suppose if we need to have analysis of the input, if the input is given to NMOS and expecting the output, its output is, it's not exactly same as required. It will be depending on the PMOS, because the PMOS is always on. If we turn on NMOS also, then output at this point will be the voltage divider output, because PMOS also is on and NMOS is also on. Then output at this point, output of the circuit will be the voltage divided by output, which is not the exact required. So this kind of faults we call it as fault model at the transistor level. This can happen once or whenever PMOS is on during manufacturing, or another way, the NMOS can also be on, which is not noticed by the manufacturer or at the design time. So these kind of models can give the errors, defects for the chips. The next topic is scan design. This is also kind of a DFT, design for testing. The fault models and the fault detection techniques what we discussed so far work well for combinational circuits. But the fault models are difficult to adapt to detect the faults in the sequential circuits like registers and other storage elements. In order to solve this problem, scan design techniques are used by modifying the registers to allow them to be chained as shown in the figure. So here there will be there can be a registers and scan in is the input which has to be scanned in all the registers by application of control input test mode, which is nothing but scanning all the registers for a detect for an error to detect. So another kind of DFT is boundary scan. It's an extension of scan design used in testing the connections between the chips on a PCB. Example is the JTAG, which supports automatic testing of individual chips and PCBs containing multiple chips. So next kind of DFT it is built-in self-test. It is a circuit capable to test itself. Best techniques involve adding test circuits that generates test patterns and analyze output responses. The advantage of a Bist embedded system embedded in a system since Bist is embedded in a system, it can generate test vectors at full system speed. This significantly reduces the time taken for test. Bist hardware remains available during the operational lifetime of the system and can be used for testing whenever the system is in the field. These are the advantages of Bist. So architecture of Bist is test pattern generator given to the circuit under test, and the output will be the output response analyzer. This is the generic diagram for Bist, in which circuit under test to be tested. For that we require test pattern generator to test for all the combinations, and the outcome will be the response analyzer. So this is the basic architecture for Bist. Now we'll be discussing about different kinds of bits or different kinds of test pattern generators used in built-in self-test. So this figure shows a 4-bit linear feedback shift register generates the pseudo-random test sequence. So taken with the 4 flip-flops. Suppose if we start with the value 1 1 1 1 by loading all the flip-flops with 1, and then if we use this circuit for random sequence generation, so this circuit can provide the sequence of 1011, then 1001, 1000, 0100 0010 0000, so on back to the four ones. So this is the one kind of a pseudo random sequence generator used to generate the 4-bit test vectors for all the combinations. But there is a gap here. The circuit is failed to create test vector for all the 16 combinations. Since we are taking 4 inputs, 4 flip-flops, 2 power 4 is equal to 16. For every clock after loading an input, for every clock we can analyze the circuit, will provide this sequence. But there is no 16 combinations. As you can count here, it is having only 1 2 3 4 8 plus 4 12 plus 3 15. So one combination is missing. So this is the disadvantage of linear feedback shift register, which is generating pseudo random but not all the combinations. To overcome this, we can use complete feedback shift register. The circuit is modified like this by using XOR operation, and by starting with any value by application of preset, and upon application of clock, the circuit can produce the sequence of 16 combinations. And for 4 inputs, 16, all the combinations are available, which can be used for testing a circuit. Similarly, we can have for 2-bit, 3-bit, 6-bit, 8 bits, and we can design a circuit with different combinations. We have implemented with XOR. We can use different combinations as well. So one more kind of circuit is, it is multiple input signature generator. So in this case, instead of loading the value using preset, we are having multiple inputs combination and looking to generate for sequence of all the combinations with multiple inputs. This is the advantage of multiple input signature register over the linear feedback shift register and complete feedback shift registers. So these are the different kinds of bits used for design for testing. Thank you.